In assignment 8.6, we're practicing free response questions from the 2013 AB Calculus exam. This question I think is pretty straightforward. A particle is moving along a straight line and our window can be restricted from 0 to 5. The velocity is given by, so we're not given position, we're given the velocity function. So we're going to put that in our calculator. And you can right away restrict your window to 0 to 5. So let's take a look at what this function looks like. Let's get our calculator visible here. So I've already put the function into the Y editor, and if I did zoom standard F26 to get a first view, if you're never sure of windows, we know we want x's to go from 0 to 5, but what do we want the y coordinates to go to? So in the interval from 0 to 5, you can see that our y coordinate looks like it's going to go down to infinity here. So we really only need this section of the graph captured. So you might say, well, this window is perfectly fine, or you might want to zoom into a smaller window. That would be your choice. So for example, I might go from negative 0.5, and I missed my negative sign there, negative 0.5. Remember that our x window is set here by our given, so we want to go to at least 5. So you might go a little bit larger than that, or you might just stop at 5. And we could see that our y minimum was quite low, but we don't really need to see anything farther below that negative 10. You could, if you wish, change that to a negative 20 to see a bit more. And it didn't go as high as our screen here, so we might make that y max smaller. But again, lots of different options there for your window size. So we've got a good picture of what's happening with this velocity function. And our first question says to find all the values of t between 2 and 4 for which the speed of the particle is equal to 2. So there we're being tested on whether you realize the difference between speed and velocity. And of course, speed is the absolute value of velocity. So we want to know when the velocity is equal to 2. That's the same as, or when the speed is equal to 2 is the same as saying when is velocity equal to positive or negative 2. So a couple different ways that you could do that. But we could, as you saw in our first problem, we could put horizontal lines there at 2 and at negative 2. And then we could find the intersection point. So if we go back to the graph, we'll see that there are 2 times between in our interval. Oh, we wanted our interval to be just 2 to 4 right now. So I could have reduced the window. So actually, perhaps all of these intersections aren't going to be within the time frame we're looking for. And if we find our intersections here of the positive 2 and the negative 2, you might right away, to avoid confusion, have gone to the window and said, well, for this point, let's actually go from 1.9, which I can't type here, 1.9 to 4.1, and then you'd be able to see even more precisely in your graph how many of those intersections we actually needed to find. So our line, our horizontal line at positive 2 looks like it's only going to intersect once in that interval, and our line y equals negative 2 is only going to intersect once. So these would be the 2 places at which the velocity is equal to positive 2 and the velocity is equal to negative 2. So I trust that you remember how to find intersection points. So pause the video, do that for yourself, and then let's get them recorded. It's interesting to note here that we don't have any units either of distance or time. One thing we hadn't noticed here was we had an initial position, though, of 10. So let's remember that. That's going to come up at some point in the problem. All right, question B says write an expression involving an integral that gives position. Oh, here it is. This is where we're going to have to find the position. So our net change theorem, remember, if we accumulate the area under the velocity curve, it will give us the position, the displacement, in other words. So we're looking for the position at time 5. So its position at time 5, s of time 5, would be equal to its starting position plus, then we accumulate from 0 through 5. We accumulate the velocity, not the absolute value, because we want the displacement here. And now, oh, sorry, I think I'm jumping the gun. First, we're supposed to write a general expression for all times. So let me do a little erasing here. That's a little too specific. First, we want to write this generically. So the position at any time t would be the initial value, where did it start, plus its displacement from 0 to t. So now I want to have a new variable here for our velocity function, since we're using time in our accumulator function. All right, and now we want to specifically use that function to find out its position at time 5. And again, let your calculator do all the work here. So we're going to, and you could do this in the home screen here, to accumulate 10 plus that integral. Let me pause and grab the calculator. So you can look at my calculator screen. So we wanted 10 plus the integral of y1 of x, that's our velocity function, with respect to x from 0 through 5. So our position at time 5 is negative 9.207. And moving on to part C, find all times t in the interval from 0 through 5 at which the particle changes direction. So remember that it can only change directions when the velocity hits 0, but then we also have to verify that it crosses over the axis rather than having a bounce point. So when does our velocity function hit 0 and change signs? Well, I think we could see that from the graph screen we saw a minute ago, but now I want to, I guess, be smart enough to change my window back. So let me escape out of there and let's get back. Remember that my graph was in the window from 2 to 4, so if I go back to the window we wanted for the original problem from 0 to 5, so I had something like negative 0.5 to something bigger than 5. All right, so looking at our graph, we can see that velocity changes from negative to positive right here, and velocity changes from positive to negative right there. So, by the way, just a calculator reminder, if you don't want to see those functions, you don't have to just delete them. You could do F4, remember, to uncheck them. So if you don't want to see those horizontal lines again. So what we really need to find on our calculator then are the zeros. So where does it cross? Where is the velocity function crossing? And then we want to be specific to say that it changes from negative to positive here and from positive to negative. So remember, our F5 choice 2 is how we find a 0, and we simply say what function we want, and I'll do this second one since we're close, and then you just simply get to a lower bound and move to an upper bound. So left side of the 0 and then right side of the x-intercept is the 0. And you're going to do that for both of these. And notice the y-coordinate is darn close to 0. It's as close as the calculator could get. So we'll just leave that as if it is 0. So we're going to take these two x-intercepts. So you're going to find both of them. And I'm going to pause and write that. So take care when you write your answer here that you show that you looked for the zeros of the function, and then that you didn't just say that the velocity changes signs. They want to know that you looked at this specific graph instead of just taking a shot in the dark at it. So that's why they want you to specify that you saw that at one of these places velocity changed from negative to positive, and at the other it changed from positive to negative. So please make sure you include that in your justification. Again, it shows that you were actually doing the problem, not just guessing at the answer. All right, one more part here. Let's look what D is asking for. So far, this has been very straightforward. Is the speed of the particle increasing or decreasing at time t equals 4? So remember that speed is unsigned. So you could be speeding up if you're going in the reverse direction. You can speed up if you're going in the positive direction. So speed, the question here is, do velocity and acceleration have the same sign? So we're interested at time 4. So we want to find out what we know about v of 4. That's just a home screen question. And acceleration at time 4, that's also a home screen question because we can just do the derivative of v of 4. And then we can compare the signs of these two values. So let's take a look at doing that. So in the home screen, if I want to find v of 4, that is just my y1 of 4. And I will do green diamond, enter. So I have a negative 11.4758, close enough. And then back to my calculator. How can I do the derivative in the home screen right away? I could do this in one step. I could get my derivative symbol. Derivative of y1 of x with respect to x, and close the parenthesis, and then use this such that. You can do this all in one step. Such that, that vertical bar right here under the equal sign, such that x is equal to 4. And if you haven't used this, we'll do a green diamond, enter. So you can see the notation, the derivative of y1 of x such that x is equal to 4. And we have our negative value, so they're both negative. I'm going to transfer that number onto my paper here. Negative 22.296 or 57, however many decimal places you want. And then I might add here that, kind of obvious, they're both less than 0. So we can say the speed of the particle is increasing since velocity and acceleration have the same sign. Since v of 4 and a of 4 have the same sign. Or should we name those? That might even be a little more precise, since I already called them v of 4 and a of 4. So we might even be more accurate here if we show that we know these are velocity